Hello, physics research, and this is my paper on 1994, theoretical modeling of thulium-holmium continuous fiber laser, and a model in which a model uses iteration technique along with our own measured transition data, shows good agreement with the experimental result. The model provides the optimum parameters for experimental verification of some research. Introduction. Advances in fiber manufacturing and doping of rare earth material elements in the fiber, and also discovery of new classes. And then fiber is a new class of laser gain medium. So there are fiber manufacturing techniques, doping technique, and a new classes as ZBLAN. And then it is the new kind of fiber laser as a gain medium in the lasers. So it's a highly efficient system. Uh, this is that the strong energy transfer mechanism between thulium and holmium, and then we can be able to get a 200% quantum efficiency. For one photon, you can have two different photons. So this is a 200% quantum efficiency. How many output photons from a single pump photon? So 60% slope efficiency. So how much will be energy you can be able to get out of 100 units? Capable of diode pumping. So ZBLAN, this is the fiber. So doped with the 4.68% of thulium and 0.1% of holmium, which is a 4.6 gram in 100 gram of a solution, which is this amount. So thulium holmium laser system is a 200% quantum efficiency due to energy transfer and cross relaxation process. Number two is a low threshold, so it can give energy at a low pump power. High slope efficiency, which is 60%, and easy energy delivery because of the guiding principle of the wave of the fiber. It uses in radar and communication, optics, and laser medical use of the fibers. Next is energy level and transitions. In this model, the dopant ion interact with the radiation field and undergo transition between the various energy levels with the characteristics probability rates. So laser material as a series of the points, they consider as a series of the point along the fiber length, and variables are the population density distributions, photon density at each point, and transition between the levels. So the pump photons density is Pz, and the signal photon density is Sz. So P for pump and S for the signal. So this is input, this is output along the length of the fiber, which is Z. So three nested program and three different equations because of two from the thulium and one from the holmium. So this is S41, S42, S21, and this is cross relaxation, 1, 2, 3 levels, and 5, 6 levels. And this is up conversion, and this is energy transfer. Now, if you consider the equations, so this is our absorption pump signal. So this is probability, C concentration, and cross section, and the number of density at N1 and cross probability and N4. So this is cross relaxation, this is absorption of the pump photon, this is energy transfer, and this is laser action. So these are the equations of, this is equation number one. Similarly, from this one is a time Uh, if you have a S, which is S42, S41, S21, S56. These are the pump, and this is a cross relaxation, and this is the laser action. So this is equation one and equation two. This is equation two. This is equation one, and we can solve these equations from the rate equation from equation one and two. So d and 4 by dt, and this is up conversion, and this is d and 4, d and 2, d and 6. So these are rates. So equation 3 and branching ratios, so which will be n1 is equal to thulium plus minus this one, n3 is 0, and 5 is homonym to this one. Equation 4, and then the rate of this one d by along the z, and we can have these two equations. So positive is amplification, negative is absorption, n1 is very large than n4, n6 is fa into n6 is fb on n5. So this one, then iteration process, iteration technique. This is maximum pump power is initial, minimum pump multiplied by transmission to the pump input. Pump forward is a pump multiplied by TPI plus TPR reflected. So PF0, that will be given by this one. So pump multiplied by TPI. So this will be given this one. SFR is 0, and then we can have this relationship to the pump photon differential equation and solved by the Runge-Kutta method. Gradient at the point is given by this two average. Zebulon fiber, one length, core diameter 6.5, 2.08% and 0.1% reflectivity. This is this one. The pump wavelength 8.818 nanometer, threshold is 8 milliwatt, slope efficiency 51% can be achieved. So this is the modeling technique. Conclusion: model of the laser action developed in the thulium fluoride fiber by constructing the rate equation and the simulating the appropriate transition processes. Cross relaxation and energy transfer have been considered in the modeling. Modeling result agree with the experimental result. Future modeling will extend to the double glide fibers. So this is my first paper in fiber lasers. So questions of this one can be asked on this one. How does the modeling estimate the performance of the thulium ammonium doped fluoride continuous fluoride fiber at 2000 nanometer uh, output, 2 micron? What are the mechanisms of cross relaxation, and energy transfer considered in the theoretical model for the laser operation? How the model determines the optimum parameter of the fiber for configuration of efficient fiber laser operation? How does the model predicts the threshold and the slope efficiency excuse me, for thulium laser system, and how do these prediction compare to the experimental results? So this is the uh, research on first paper on fiber laser.